in the previous class, I mentioned that we were talking about resonance, okay, and so resonance occurs when something is forced to oscillate, okay, in its own natural frequency lah. Okay, that's the basis of this. Okay, something that is like not doing anything, suddenly it's forced to oscillate, dia dipaksa untuk berayun, okay, at its own natural frequency. And so I thought I wanted to demonstrate this to you, and you can actually try this at home if you want. Okay, if you have a guitar lah. Okay, so if you have a guitar, so you know a guitar has sorry. Okay, so a guitar has 6 strings, right? So you hear the 6 sounds lah. Okay, I don't know if you can hear this, but hopefully you can lah. Okay, so this one is the one with the low frequency at the bottom over here. Okay, and then the one at the highest. Okay, this is the one with a high frequency. But because there are 6 strings on a guitar, okay, 1 2 3 4 5 okay, that means there are 6 different frequencies lah. Okay, and then of course the combination of the frequencies is what gives you what we call the chords. Okay, so for example, C chord will be sorry. So a C chord will be, oh no, sorry, too early in the morning. Okay, so this is a C chord, combination of different frequencies. Okay, when you put it together, it will sound, it will make a nice chord lah. Okay, but if you think about it in terms of science, it's just a combination of different frequencies playing at the same time. Okay, so frequencies that clash, for example, okay, things like this lah. Oh no, this is not so. Sorry. Oh no, sorry, this is worse. Okay, for example, like this. Okay, so these are clashing frequencies lah. Okay, they are like sound almost the same, but they're not the same, and it creates kind of like a very weird sound. Okay, so it's like you weird. Okay, although nowadays definition of music is very variable, so it can always change now. But let's talk about resonance. Okay, so to demonstrate resonance to you, let me stand up now. If you cannot hear me, this one lah. Okay, so oh my goodness. Okay, so what I have here is I have this small piece of sticky tape. Okay, actually it's just a piece of paper lah. Okay, it's just a small piece of paper, and I'm going to put this piece of paper on one of the strings. Remember, every string has its own natural frequency. So this first string over here, this is the natural frequency. Okay, this one, okay, natural frequency. So everything is different natural frequencies now. Okay, and what I'm going to do is I'm going to put the paper on the, let's say the 3rd string lah. Okay, let's say over here. Alright. Wait. Okay, I'm going to put the paper on the 3rd string. I've never done this online, so okay, here. So the paper is here on the 3rd string. Yeah, I don't know if you can see this. Okay. So paper is on the 3rd string. But I'm going to play the 4th string. Okay, which is this one. The one that is not touching the paper. Okay. Oh, sorry, hold on. I just blew on the string. Sorry. Okay, so I played the 4th string. Obviously the paper is not going to move lah. Okay, can't you see? Okay, playing the 4th string when the paper is on the 3rd string. But let's say I increase the frequency of the 4th string, okay, by pressing on the 4th string on this side. Okay, so you're going to find that this 4th string over here, okay, as I play, I'm going to increase the frequency lah. Now what I want you to notice is, look at this piece of paper as I'm increasing it. Okay, let's see what happens. Okay, so, oh sorry. Do you notice that the paper moves on its own? I didn't touch it at all. And I'm definitely not blowing on it. Okay, let's see again. So, paper is on the 3rd string. I am playing the 4th string. Okay, you don't believe me? You can zoom lah. So, paper's not moving. Paper's not moving. Paper is starting to move a little bit. Oh, sorry. Okay, and this one, paper moves the most. Okay, and do you know why the paper is moving? Because the note that I'm playing now on the fourth string is the same sound as the one as the third string. Almost the same. So when I play it on the fourth string, I am making this string vibrate at a frequency. And it causes this string, the third string that I did not touch at all, to vibrate on its own. And how do you know that it's vibrating on its own? Because the paper is moving. Let me show you again. Allah, this paper. Let me show you again. Sorry. So being forced to oscillate on its own, okay, is what we call resonance. Okay, look, so like, okay, paper not moving because not resonating, no resonance. But when there is resonance, I'm playing the fourth string. Sorry, I'm playing the fourth string. I shouldn't be blowing down the paper. I'm playing the fourth string, but the paper is on the third string. Okay, once again, you can try this at home. Actually, you will be able to see. This is how people tune their instruments, lah. So when I play the fourth string, paper is on the third string. Okay, you find that the paper moves because, and why does the paper move? Because the third string is vibrating on its own, while although I'm actually plucking the fourth string. Okay, and if you put your finger on the string, you can actually feel it vibrating itself. So this is an example of resonance, okay, where this thing is oscillating and is forcing this string, the third string, to also oscillate at its natural frequency, because I'm playing the same note as the third string's natural frequency. And I can do it with all the other strings also lah. For example, okay, this is the first string, but the second string has the same sound. Okay, the second string is an open string lah. Okay, oh sorry, second string is an open string. Okay, so the same sound, playing the same frequency as this one. So this, what's going to happen to this string is it's also going to vibrate, and this is what we call resonance lah. Okay, the string that is tidak kena sentuh langsung bahkan is being forced to oscillate at its natural frequency because there's something else outside that is already vibrating at its natural frequency. Okay, so give this a try. If you have a guitar at home, it's always good to give it a try. Very simple. Just one piece of paper and a guitar. Right, let's begin. Complete the sentence below by ticking the correct box. Okay, the wave produced by a slinky is which one? Transverse or longitudinal?
Transverse.
Okay, it's a transverse wave lah, because the movement of the wave, the propagation of the wave is this way, but it is perpendicular to the movement of the molecules. Okay, all right, on diagram 1, mark X on any crest of the wave. Okay, you can mark X over here as long as you know what is the meaning of the word crest. Okay, that's the most important thing lah. Yang atas itu adalah crest, and then yang bawah itu adalah trough. Okay, remember these two words are very important terminology when it comes to waves. Okay, not high point, low point. Okay, that is noob speak. Okay, only noobs will talk that way lah. High point, low point. Okay, crest and trough. All right, next, complete the following sentence by underlining the correct phrase in the bracket. The direction of the hand movement is beyond.
Perpendicular to.
Very good. Okay, the direction of the wave movement. This is done lah. Okay, what is transferred by the wave, Trevor?
Kinetic energy.
Oh, okay, very good, even better. Okay, but basically it's energy lah. But yes, I think kinetic energy is also a good answer. Although, hold on. Okay, fine, can. All right, next question. Choose the correct path for one oscillation. Tick X in the correct answer in the box provided. Natasha, Nikki?
The third one, PQRQP.
Okay, PQRQP. Oh, I like the sound of the bird at the background. Okay, one complete oscillation. Okay, must go back and forth. Please tell me when Diana comes back. I have to call Diana next. I saw her, but Just before Nikki, she disappeared. Suspect. Okay, anyway, question B. The stopwatch in diagram 1.2 shows the time taken to make 20 oscillations. Okay, so strange that the timer will show here, but this is showing here. Okay, based on diagram 1.2, state the smallest division of the stopwatch. Jenny?
Sir, what is smallest division?
Okay, thank you for the question. I think that's a very good thing to ask. All right, smallest division means, okay, so all these lines here are what we call divisions. Okay, so sometimes in certain instruments, like for example, your ruler, okay, there is a big division. And there's a big division like this one marked by the big line. So you know that if this is 12, this is 10, and this is 15, and there is 1, 2, 3, 4 before the 15, right? So you know that each big division this is 11, this is 12, this is 13, this is 14, this is 15. So that means the big division, okay, the big division is 1 second lah, because every big division is 1 second. But on the stopwatch over here, there is an even smaller division that is next to the big division. Right? And how many lines are there? There is 1, 2, 3, 4. So there are 4 lines, until between 10 and 11. Okay, so how many seconds do you think each line represents?
0.2.
0.2. Okay, and that's exactly the answer for the smallest division of the stopwatch. Anyway, this one becomes 10.2, the next one is 10.4, 10.6, 10.8, and then 11.0. So that means each small line represents 0.2 seconds. This is a very, very common question, and we can learn from this. Okay, so the smallest division is the value of the smallest line. Okay, and you have that actually in your ruler. Don't know if I have my ruler with me. Hold on. If you look at your ruler, sorry, my horrendous ruler. Okay, if you look at the ruler, so you have the 8 and you have the 7, and then you have the big division, right? Okay, and then the small division, there is 1, 2, 3, 4, 5. So you know that each of the small divisions represents 0.1. That's why you can get 15.1, 15.2, 15.3, because the smallest division is 0.1. Okay, so it's a good thing to recap this, okay, and to revise this. These are things that I think is covered in Form 1, Form 1 plus, sorry, in Chapter 1, but you may have forgotten. Okay, the word division. Okay, Chen-Yi, since you asked me this one, can you also answer the second one? What is the time taken for 20 oscillations?
45 seconds.
Okay, it will be 45 seconds. Now, because there is a decimal place in the division, okay, because there is a decimal place in the division, the division tells us two things. Number one, how many decimal places all your readings must take. That's why you see here there is a 45.0. Actually, if you just see this, it's memang 45 kan? Okay, we will say it as 45. But in physics, we have to be true to the instrument. Okay, if the instrument has one decimal place, we must make the 0.0 exist. Okay, so that's why this answer here is 45.0. Okay, so that's the number one implication. Number two, if your smallest division is 0.2, you cannot get this kind of answer, 10.3, 10.5. It cannot be shown over here. So your answer must be 10.2, 10.4, 10.6, and so on and so forth. 15.2, 15.4, okay, 15.8, all these can. But if you write your answer 15.7, cannot. Why? Because your smallest division is 0.2. 0.2 means you cannot have a 0.1 or 0.3 kind of answer. Okay, but whenever I say this, always will have students they will ask me, but sir, What if the pointer here ngam in the middle of okay, for example in the middle of 13.6 and 13.8. It is not 13.6, it is not 13.8, it is ngam in the middle. Okay, so if when this happens, okay, I'm telling you it will happen lah. Okay, it does happen and I've seen it a lot of times. Now when this happens, my answer is usually you have to make a choice. Okay, the one thing that you definitely cannot write now is 13.7. Okay, definitely you cannot write that. Why? Because there is no such thing as 13.7 on your stopwatch. There's only 13.6 and there's 13.8. Okay, the stopwatch cannot show you a reading of 13.7. Okay, so in this case, whichever one you choose is correct. You just make the choice lah. Okay, you want it to be 13.6 under or you want it to be 13.8 over. Okay, just like ruler, I always see this all the time with ruler. Okay, let's say this is 1 and then this is 2, right? And then 1, 2, 3, 4, okay, then 5. This is 1.5, 6, 7, 8, 9. Okay, and then the thing that you want to read, right? The one thing that you want to read, ngam, it falls over here. Oh, so you want to give what? 1.45. Can your ruler tell you this reading, 1.45? Cannot. Because the smallest division in your ruler is 0.1. It can only tell you one decimal place and definitely not 0.5. 0.05 cannot. So if you have this kind of situation, what do? You make a choice. Okay? Does it look more like 1.4 or does it look more like 1.5 to you? You have to make the choice. And whichever choice you make is going to be correct. Okay, it's just suka hati kamu mana yang kamu mau. The choice that you should not be making is the choice to do this kind of reading. Because this and this smallest division doesn't make sense. Okay, if you give me this kind of reading, I will say, can you show me your ruler? Show me where is 1.45. You cannot show. You cannot show with any certainty that there is 1.45. So it is better to make a choice between 1.4 or 1.5. Don't, okay, I'll be safe, take the middle route. No. Okay, don't play it safe. Okay, make a choice, people. Okay, life is all about choices. And sometimes when both are good choices, just make a choice. All right. Okay, thanks, Chen Hee. Good question. What is the type of the physical quantity for time? Take X in the correct answer provided. Can I have Diana for this, please? Diana, can you answer question C? Oh, time vector quantity. Cannot be. Vector quantity is what? Vector quantity must have magnitude and direction. At this point of your study in physics, time got no direction one. Okay, you cannot say negative time and positive time. Okay, so we call it a scalar quantity. Okay, these are all basic stuff. Everybody, please make sure you get this. All right, question number 2. What type of wave is this water wave? Aerial, transverse, or longitudinal? Okay, this will be transverse wave. Very good. Okay, dalam bahasa Melayu dia dipanggil gelombang melintang. Walaupun saya tidak faham kenapa dia cakap melintang, tapi tidak apa. Okay, the next question. Oh no, sorry, we haven't come. Okay, yeah, the next question is something that somebody asked, and I realized that you actually haven't learned this lah. Okay, now if you take a look at this shape of the wave, it kind of looks like a lens. And it kind of looks like a lens, but on one side only lah. Okay, now what happens to these 3 light waves is that it's going to meet in the middle. Okay, it's going to meet in the middle, and that's why when you have a combination of 3 light rays that meet together, it's going to produce a very bright spot. Okay, so what you draw is you just draw here and you draw here because of the shape of the wave. The shape of the wave like this, okay, going up, okay, it's going to converge in the middle. Okay, so to show how a bright region is produced on the screen. So the question is, how come this one is dark? Okay, because okay, let's say I have another two rays over here lah. Okay, what is going to happen is this ray is going to go out here and this ray is going to go out here. Okay, it's going to spread out. Okay, so interesting, if the wave is a crest, okay, it's going to focus. Okay, it's all going to focus on one place. If it is a trough, okay, it's going to spread out. Okay, and that's why the places where the light focuses is bright, and the places where the light spreads out is dark. Okay, and if you remember in the ripple tank that we saw the other day, we saw that the bright spots okay, the bright spots are very thin, and then all the dark spots over here, sorry, pen color black. Okay, all the dark spots are very wide apart. Right? They're very like wide apart. Only the bright lines are very thin because the three rays, the three representation rays have already focused into one place. Okay, that's why the bright places are very nipis and the dark places are very wide. Okay, because of this effect lah. Okay, and if you want to know, okay, this is what we call refraction. Okay, we will study this in chapter 6, but this is called refraction of light. Okay, so when light refracts, it will either focus or it will spread out. Okay, we will talk about this in chapter 6. All right. I hope that the person, unfortunately, the person that asked me this question is not here, but you watch the recording. Okay, mark one distance which is equal to the wavelength of the water waves. Okay, the wavelength has to be either from bright to bright or from dark to dark. Okay, also can. So this is one wavelength, or this is also another wavelength from one crest to another crest. Sorry, please extend this a little bit. Okay, or from one trough to another trough. Okay, so all these are all marked by the word lambda. Okay, stop saying, I don't know what is it in Chinese, 人 terbalik. I always hear this one, 人 terbalik. Okay, diagram 6.7, 6.1, 6.2 show the water droplets drop onto the water surface of a basin like this. Okay, the static images of the water droplets were from both tabs were taken at the same time. Okay, take a look at this, take a look at this, and then after that compare it with this and compare it with this. Okay, now let's underline the correct answer in the bracket to complete the sentence below. A wavefront is a line joining all the points which have the same ... Rahman.
Velocity.
Velocity, no, it's the same phase. Okay, wavefront is same phase. Same phase maksudnya like that. Okay, dia bergerak bersama-sama. Okay, if it is not the same phase, is I cannot even do not the same phase. How? One is going up, but the other one is going. Okay, so like that. Okay, so this is not the same phase, but if it is moving together, okay, it is in phase. We call it in phase lah, same phase. Okay, so yeah, so obviously I'm not a very good dancer lah. Let's not talk about that. Okay, number B. Compare. Okay, this is something that I always emphasize. Everybody, okay, whether you are a good student or not a very good student, everybody must know how to compare. Okay, so let's begin comparing. Meryl, can I have the first comparison? Compare the depth of the water in the basin.
The depth of water in the basin in diagram 6.1 is same as diagram 6.2.
Okay, good and excellent answer. All right, but for short form purposes, I'm just going to say same lah. All right, the number of water droplets dripping at the same time. Can I have the next person? Kahal? 6.2 higher than 6.1. Okay, yeah, 6.2 is higher than 6.1. Don't forget, if this is exam, please write in full sentences. Okay, the number of water droplets in diagram 6.2 is higher than the number of water droplets in 6.1. Okay, but since you're just tutorial purposes, it's okay to write the short form lah. But for exam, remember, I emphasize writing in full sentence for comparing. Okay, and there are reasons why I do this. If you want to know, I will explain to you next year, okay, when you're in Form 5. All right, next, compare the frequency of the dripping water, okay, from the taps. Joey, is Joey the next one? Yeah, should be Joey. Yes, Joey.
The frequency of the dripping water from the taps in diagram 6.2 is higher than 6.1.
Okay, very good. Okay, another excellent answer. All right, compare the wave frequency is 6.2 is bigger because there are more drops, there are more titisan air pada waktu yang sama. Okay, so the more droplets you have, the frequency is bigger lah, as you can see. Remember in the interactive I said, if the frequency is higher, the wave will look like this. While the frequency is lower, the wave will look like this. Because there's less waves in 1 second. Okay, that's why the frequency in 6.2 is higher because there are more waves, okay, at the same time. All right, compare the wavelength of the circular wave, which is spreading outwards in the basin. Ivers. Oh, the wavelength on diagram 1 is bigger than the wavelength in diagram 2. Excellent. Okay, see, very easy, right? All you have to do is just open your eyes and see. Anybody can do compare. Okay, of course, this answer is 6.2 is lower, but the meaning is the same. You have the right meaning. Okay, I would probably just adjust it into diagram 6.1 and 6.2. Be specific lah. Okay, Ingwei, because this is 6.1 and this is 6.2, not just diagram 1 and diagram 2. But the idea is there. Okay, good. All right, relate the frequency of the dripping water to the wavelength of the circular wave. Can I have Ethan for this?
The higher the frequency of the dripping water, the shorter the wavelength.
The higher the frequency of the dripping water, which is this, the shorter the wavelength. Okay, good. I want you to ignore this answer, except that, okay, so if you heard Ethan's answer, okay, so you said frequency higher, okay, wavelength shorter. Okay, now I want to just emphasize this, and this is Sir Marcus punya rule lah. Okay, I like the fact that you use the word higher, very nice. Okay, but I would not advise you to use the word shorter. Okay, you can always say lower, smaller. These are safer words to use. Okay, because again, the comparing question, the relating question is all across the board. Every chapter will have these kind of questions. Okay, so I always tell my students to use the safe words, which is bigger, smaller, okay, higher, which Ethan used just now, lower, and another one for bigger and higher is also greater lah. Okay, these are, after a while, okay, when you go into Form 5, you will realize that I will only emphasize these words. I don't really encourage the use of the word shorter, longer, faster, or slower. Okay, and definitely heavier. This one heavier memang out lah. Okay, I can tell you with 100% certainty that these two words are definitely not accepted. Okay, for whoever is the examiner lah. Okay, but for me, I would prefer if you use, instead of the word shorter, which actually the meaning is there. Okay, the meaning is there, but the problem with exams is that you have to follow the exam rules lah. Okay, and in the exam rules, okay, or at least in Marcus's exam rules, okay, Marcus doesn't like to see the words. Marcus doesn't like to see these words. Okay, Mr. Marcus only likes to see these 5 words. Okay, yes, call me cerewet and fussy if you want. Okay, but I'm thinking, saya berfikir jangka masa panjang. In the long run, this is always better. Okay, so I would adjust your answer to be the higher the frequency, excellently done. Okay, the smaller the wavelength, or the lower the wavelength. It's okay, because the word lower doesn't mean that it is shorter. It just means that it is lower in number. Okay, all these are bigger, smaller, higher, lower, greater. Sorry, all these are comparing the number. Okay, you can calculate the wavelength. Anyway, this is a very long explanation for something that I've already mentioned so many times. Okay, in short, please avoid using these words. Okay, I really strongly advise against using these words. Okay, but if you really still want to use it because you think that English is more important than physics, then okay lah, go ahead lah, use it at your own risk. Okay, I will not be responsible if I mark it wrong. All right, next question. What happens to the wavelength of the circular wave if I reduce the depth of the water in the basin? Chloe?
The wavelength decrease.
Sorry, what did you say? What is the last word?
Decreases.
Okay, very good. The wavelength will decrease. It will become even more shorter. Why?
Because the bigger the depth of the water, bigger wavelength.
Okay, that's like a roundabout way of saying the same thing, right? Okay, let's think about this. Okay, I think that's a very good attempt now. But let's talk about this. The depth of the water, okay, affects the wavelength lah. Okay, because so what are the things that can affect the wavelength? We come back to the wave equation. The wavelength is affected by two things, which is the frequency of the wave and the speed of the wave. Now, obviously, in 6.1, the frequency is the same. Okay, so the frequency has not changed. So the only other possible explanation is that the speed of the water waves has decreased. Okay, because the water is shallow. And we know this, well, if you've ever been to the beach, you will definitely know this. When the water is deep, right, at deep waters, the wavelength is very big. Right? But as you get nearer and nearer to the shore, the wavelength becomes even smaller. Oh, sorry. I'm not supposed to change the amplitude, sorry. Okay, the wavelength becomes smaller. Okay, so this one is deep water. Okay, this one is shallow water. Can you imagine if in the deep water, the frequency also is very high. Okay, can you imagine if in the shallow water, the wavelength also is very short. And you go on the boat, you'll be like this, you'll be always like that all the time. But if you've ever been on the boat, right, let's say you go to Pulau Sapit or Pulau Manukan, you will feel that as you go up and down, right, the intervals become longer and longer as compared to at the very beginning. At the beginning, it'll be like because the wavelengths are short. Okay, but the deeper into the sea you go, the wavelengths become longer. I'm not talking about the strength of the waves. Remember, the strength of the waves is because of the amplitude. That's a different story altogether. I'm just talking about the wavelength. Okay, so the wavelength, is determined by the speed of the water waves. Okay, the wavelength decreased because the speed of the water waves has decreased because of the position of the water. In deep waters, the speed of the wave is much faster. In shallow waters, the speed of the wave is much slower. That's why when you stand at the beach, it is safe to stand at the side of the beach. Okay, wow, I missed the beach. Okay, anyway, it is safe to stand at the side of the beach because the waves that are coming in are pretty slow. Okay, as compared to if you go into the deep water. Okay, the speed of the water waves decrease because of the shallowness of the water. All right, let's continue. Carlson, underline the correct answer, please. Sound wave is a
Longitudinal.
okay, longitudinal wave. Okay, I've heard this. I've heard somebody, not this class lah, but I've heard people in videos they pronounce this as longitudinal. I'm actually not very sure whether it's longitudinal, but I would think it's longitudinal. Okay, anyway, uninteresting info. Okay, X region, Bernardine.
Compression.
Okay, very good. This is a compression region. Mark one distance. Okay, this will be the distance from one compression to another. Now, if you're going to mark the rarefaction, okay, it will be like this. Mark the center of the rarefaction to the next rarefaction. Okay, now the tuning fork in diagram 1 vibrates in water. What happens to the speed of the sound? What if the question is what happens okay, what happens most of the time, which is like 90% of the time, there are only three possible answers that you can put. It is either increase, or it is decrease, or it is unchanged. Okay, so even if you don't know what the answer is, okay, but when you see what happens, set it in your mind that, oh, okay, if the question say what happens, means it's one of these three answers. Either it is increasing, either it's decreasing, or it's unchanged. If you don't know, tembak. Okay, don't leave these kind of questions unanswered lah. Okay, if you don't know, so just tembak. One of these three is the correct answer. And since Alvin is probably not here, Wong, can you please? We have to go back to Wong already.
Decreases.
Really? Yeah. The speed of the sound decrease in water. Oh, it increase. Oh, speed of sound increases in water. Do you know why? Okay, let's talk about sound now. Sound in the air. We always think that sound in the air moves very fast. Okay, but actually, yeah. Why? Okay. This is a long explanation, but I think I should do this. Okay, remember, sound waves especially, sound wave is a mechanic. Oh no. Yes, it's a mechanical wave. Okay, sound wave is a mechanical wave, which means that in order for the energy to be transferred, in order for the wave to be transferred, okay, it needs, it needs materials to be transferred. Okay, and the thing that is transferring the wave, energy is the molecules lah. Okay, now in a solid, the molecules are arranged this way, very near to one another, bahkan. So if you think about it, if I shake this molecule, every other molecule is going to shake very fast at the same time. But in water, the molecules are a little bit further apart. Right? The molecules are a little bit further apart. So if, let's say, I vibrate this molecule, if I start vibrating this molecule is also going to vibrate because, mereka berpegangan tangan lah, fine. Okay, but it's going to take a slightly longer time compared to the solid. Now, if you compare it with in the air like this, in the air like this, okay, what is the arrangement of the molecules in the air like? Arrangement of molecules in the air is much further apart. Right? So it's going to take some time for the sound waves to reach this one, and then after this one will vibrate, and then this one, the sound waves will be this one. Have you ever done the activity or the experiment now? When you were much younger, you take a tin can lah, and then after that you put a string, and then you put this one, and then you whisper into this person's ear, and then the other person put the ear over here, then you're like, wow, I can hear what you're saying. Okay, it works around that same principle because this is a solid. Okay, and if let's say you whisper, okay, into the tin cup, okay, the sound can definitely reach this one because the sound waves travel much faster in a solid as compared to in the air. Okay, this one if you whisper, here can hear one, but in the air, in the open air, let's say I stand 1 meter, 2 meters away from, let's say Wong, you stand 2 meters away from me, and then I start whispering, you cannot hear anything. Okay, or if you can hear, so it will be 2 hours later. Okay, you probably hear it because sound waves travel slower in the air. To us, it feels that it travels very fast. Okay, but in actual fact, it travels much faster in water and it travels much faster in solid. The only problem is in water is difficult for us to hear. Okay, but actually, what is happening is, let's say if you shout in the water, the speed of sound in water is faster because the molecules are nearer to one another. Okay, because it is a mechanical wave. What transfers the waves is the molecules in the water, in the air, in the solid. Okay, so the water speed, the sound speed in water, okay, will definitely increase. The sound speed in a wood, okay, sorry lah, if let's say you have a block of wood, okay, and then you bury yourself here, right? Okay, and if you speak through the wood, the speed of the sound, okay, will be faster. I'm not saying that you can hear each other clearly because that's amplitude, but I'm saying that the speed will move faster. Okay, think of earthquake. Okay, earthquake, when something vibrates, right, everything vibrates very fast. Okay, imagine if there's an earthquake in the air. You can't feel anything because the air, it takes a very long time for shaking in the air to reach us. Okay, so this is something that is kind of like is kind of like opposite to what we always think, because we always think that air, speed of sound travels faster in the air. Actually, it's not. It travels faster in water, and even more faster in in solids. Okay, let's talk about this. Can we just quickly go through this? Which of the following quantity decreases when system undergoes damping? Vian?
A.
Okay, A for amplitude. Good. Secondly, Trevor, system which produces this graph is having a
B.
damped oscillation. Oh yeah, you're right. I don't know why it marks C over here. Okay, sorry, it's definitely B. Oh no, I've given the answer to number 3. Okay, number 3 is A. Sorry, number 2 is B. Okay, damped oscillation. If it is a forced oscillation, people, the amplitude will remain the same. Okay, so mark it over here. If it is a forced oscillation, okay, the amplitude, okay, remains constant. Okay, you'll always have the same amplitude because somebody is always pushing the string. Okay, resonance will occur in this system if the energy supplied to the system at frequency is equal to the F. It must be the exact same frequency as the natural frequency. Then resonance will happen. Okay, question number 4. Oh, there's only 3. Okay, fine. Question number 4. Oscillating system experiences damping. The displacement time graph is shown in diagram 2.2. Damping is a situation where, let's go ahead to this now. Okay, its amplitude of the oscillation decreases. Okay, state one reason why damping occurs in this particular oscillating system. Okay, take a look at this system. Okay, what is the reason? Is it Nikki? Yes, it's Nikki. Nikki, why does the damping occur?
I don't know.
What causes, come on, think about this. What causes this spring or this load to slow down?
Because of the loss of energy.
Loss of energy due to?
Heat. Friction.
Friction because of?
What?
What causes the friction?
What?
What causes the friction? What is this load frictioning with?
Oh, water.
Water friction. Okay. So water friction or energy loss due to the water friction. If you look at the system will tell you, okay, if it is in the air, then it's air friction. Okay, but if it is in the water, it's water friction. Okay, if it is in your stomach, then it's a stomach friction. Okay, up to you. Okay, now remember that this is external damping. Okay, remember we talked about 2 types of damping. There's external and there's internal damping. Internal damping is really because of the molecules. But external damping depends on where you put the load. If it is in water, then the external force is from the water. Friction is from the water. But if it is in the air, then the external damping is because of the air friction. Okay, so be flexible that way. All right, good, Nikki. Based on diagram 2.2, state the period of the oscillating system, Chen-Hee.
0.4 seconds.
0.4 seconds. Okay, one period is one full wave. Okay, so 0 until 0.4, it will be 0.4 seconds. The frequency of the oscillating system, Iril. When it comes to Ariel means we have to pause already. Ariel, come on, faster. Because I don't want this to be homework. So let's like faster finish. Ariel, how do you count the frequency? What's the frequency? Quick, Ariel, quick. Ariel is like typing for his life. Faster. Rahman, Meryl, and Leong, be ready, yeah? Okay, you belum answer. All right. Never mind, let's move on. Rahman, if you know the period, how do you count the oscillation? The frequency.
2.5.
Okay, so what's your... sorry, how do you get 2.5?
1 over 0.4.
Very good. 1 over 0.4. Give me the unit for frequency, please. 2.5 what?
Hertz.
Okay, very good. 2.5 hertz, Hz. Okay, now what will happen to the period of the oscillating system? What will happen to the period of the oscillating system when a heavier load is used? Again, guys, the word what will happen. What will happen means there are only three possible answers. It will either increase, or it will decrease, or it will remain unchanged. Okay, these are all answering techniques that help you when you it's like you don't have to give a long explanation. Just one of these three words will do. Okay, what will happen to the period if the heavier load is used? Sorry, who's next? Meryl.
Increases.
Okay, the period will increase. Masa untuk satu ayunan lengkap akan menjadi lebih lama. It will become longer, which is increasing. Okay, all right. There's another one. Okay, fine. Leong. Okay, hold on, never mind. I have to show the answer immediately. You know why? Because I forgot to reorder these slides. Okay, which pendulum will oscillate the maximum amplitude is the one that is the same level as X lah, so it's pendulum M. Okay, the reason for this is it's either the same length or you can say that it is the same frequency. Okay, name the phenomenon based on the answer. It is called resonance. The period of oscillation, because it's given the frequency 2, okay, you can count the period by 1 over 2. But the unit for period is 0.5 seconds. Okay, not hertz. Hertz is frequency. Period is seconds. Okay, that means satu ayunan penuh is half a second. Okay, 1 over 5 seconds. All right. Now, pendulum X will stop oscillating. On the diagram 4.2, sketch the displacement time graph to show the damping process. Okay, the most important thing is that the amplitude decrease. I want to see the amplitude decrease, but I want you to make sure that the frequency is the same. This is a very difficult graph to draw at first, because you have to make sure that the amplitude decrease, and at the same time, you need to make sure that the distance between the crests are all the same. Okay, same distance, same distance, same distance, same distance. Okay, even I have a problem drawing this. I always draw like this, you know. The one with the high amplitude will be very thin one. And then after a while, it gets bigger and bigger. see, this is my horrendous draw. Look at the distance between the crests. Langsung tidak sama. Okay, so this is a slightly difficult graph to draw, but you need to take into account this. Because when damping happens, only the amplitude is decreasing. The strength of the wave is decreasing, but the frequency is not. And because the frequency is not, okay, and the wavelength also is not, the speed of the wave remains the same in damping. Okay, the only thing that changes is the strength of the wave and the amplitude. Okay, so if anything, these first two subtopics will teach us that actually the strength of the wave, okay, is separate from the speed of the wave. Something can be moving very fast. The wave can be moving very fast, but it may not have a very big strength. Okay, for example, if let's say a wave is like this, okay, very fast, because the frequency is so small. Okay. Oh, sorry. Yeah. Because the frequency is so big, sorry. Very fast because the frequency is so big. But look at the amplitude, it's such a tiny one. Okay, compared to this. This wave is moving very slowly because the frequency is so okay, the frequency is so little, but because of the amplitude it's going to be a much stronger wave. Okay, so learn to separate these two.